Okay, so this is Fpgas for Hobbyists. This is a talk that I have given a couple times now on FPGAs for people more or less like us, who aren't really like professional double E's who know how to do all this. I can't really make any claim to be an expert in FPGAs, so it's likely that people in here know more than I do about this. If you do, please say so if I get anything wrong. And it's also likely that in 2 weeks I'll come in and say, well, I was really wrong about that thing, and here's actually the right answer. There are already a few things in here that I'm going to be doing that to from last time. So this is also, besides about FPGAs, I wanted to focus on a good application of FPGAs. So this is about how to use 2019's technology to recreate 1987's. So, like most of my talks, I'm going to begin with an FPGA is not an Arduino. Most of us are familiar with the kind of Arduino microcontroller mindset of stuff where you're setting pins and reading data from pins, and it's a computer that runs a C-like program that's dealing with data on pins. An FPGA is not that at all. It's not even a computer, really. This is a bespoke hardware device. It's made up of what's called a fabric of standard logic elements. So you get lookup tables or LUTs, adders, flip-flops. Of course, there are I/O pins that you can tie these logic elements to, because because otherwise it'd be useless. You also get things like block RAM. All these things you could build with LUTs, but it would take more LUTs than it's worth, and like every design is going to need flip-flops, and so they might as well just give you some flip-flops and let you wire them up. FPGAs, there are three main manufacturers. Xilinx is the big fancy one. Altera is kind of like the AMD to Xilinx's Intel, which is kind of ironic because Intel actually owns Altera. And then there's Lattice, which is sort of the like Atmel Arduino AVR equivalent. I like Lattice a lot. I recommend using Lattice chips for hobbyist stuff like ours for a couple of different reasons. Xilinx's is huge and expensive. Their tools, like all these guys, if you notice microcontrollers, they seem to be giving away the dev tools for free to sell chips. With FPGAs, my impression is that it's the exact opposite. They are giving away the chips for practically nothing to sell you seats of those dev tools. They are huge and heavyweight. The Xilinx dev tools are my favorite because the free version of the Xilinx dev tools, there are two free versions. One only works with exactly one chip, but works on all the operating systems. The other one works with all their chips, but only, or up until a certain point, but only works on Windows 7. So I've got a Windows 7 VM for exactly that stupid reason. There's no reason to deal with crap like that when Lattice exists. Lattice gives you, well, Lattice doesn't give you this, but for Lattice this exists. There's an entirely open source toolchain called IceStorm, because the Lattice chipsets that it supports are called the Ice Cube series, or Ice 40. There are a bunch of different things that claim to be the Arduino for FPGAs. As far as I'm concerned, they're all lying, because the Arduino, what makes it cool is not the hardware for the board, it's the software. And the software for all of these sucks, but the IceStorm software sucks a little bit less. What was I going to say? There's also a thing that I'm not going to talk a whole lot about this because I haven't actually used it myself yet, but it's pretty cool. It's called the Mach-XO. This is a series of 3 chips that Lattice makes that are kind of halfway between a CPLD and an FPGA. The deal with Mach-XO is most FPGA chips, you need a flash ROM to store the bitstream on. Unlike a microcontroller, you can't just flash code to it and have it run it. You need to put that code on a separate source that then gets written to it. You can actually reprogram them at runtime too. The Mach-XO has some internal flash ROM for it. The downside to that is that it's also not that great of a chip, honestly, and really putting on an extra ROM chip isn't that big of a deal, which I'll get to that later. So a little bit more about Ice Storm. It has a fancy drag and drop GUI where if you want to, you can drag and drop and wire together logic elements and wires and make a design visually. You probably don't want to do that, and I'm not really going to talk about it. There is a command line compiler that's much better, though, that reads Verilog and turns it into a bit stream. And so part of what I did here was I set up a Dockerized environment for this tool that's actually on this laptop. I can demonstrate it. And it's actually a collection of other tools. So the first thing, part of what makes FPGAs intimidating is that there's a bunch of steps that you don't have to do when you're talking to a microcontroller. For a microcontroller, generally you start with C code, run it through a black box, and you get a magic board that does stuff. That's the way Arduinos work, and it's really quite simple. You plug the Arduino in the computer, click the little button with an arrow on it, and then your board does magic stuff. With an FPGA, mostly those steps that are all invisible in microcontroller are visible and stuff you gotta deal with. And I have actually, at this point in the process of making this thing, had problems in every one of these pipeline stages. So there's a reason why they're all separate. But the first one is called Yosef, which stands for Yosef's Open Synthesis Suite. This is what you're mostly going to be cursing, because it is what is reading the code you are writing. Yosef turns your Verilog, which I've got an example of what Verilog looks like over on the right here. Yosef turns your Verilog into Berkeley Logic Interchange format, or BLIF. Although it also turns it into other formats like JSON, and actually JSON is what I'm using now, not BLIF. These slides are a little bit out of date. It'll optimize your code some. There are some features that it doesn't support. Yosef's support for, I actually came across the world's worst error message the other day. Yosef's support for tri-state buffers is limited, is what it said. What I was doing, Yosef dealt with just fine. It supported what I was trying to do with the tri-state buffer, but it didn't know that what I was trying to do wasn't something that it didn't support, and so it warned me that if I had done something else, it might not have worked terribly early. But the nice thing about Yosef is there's a subreddit for it that the guy who wrote it is active on. He's also active on GitHub. If you've got a problem, send him to Verilog. He seems pretty nice, and will fix the software if your Verilog is fine and it's his software. But after you get that, BLIF or JSON is sort of like Yosef has turned your Verilog, which is a list of, which is a description of what your circuit's going to do, into a list of all of the logic cells that it wants from the FPGA. So it might say, I want to have a LUT with the following outputs. I want to have a flip-flop that is connected to this other flip-flop over here, and so on. After that, you need to send it to a place and route tool. Place and route is what takes the blocks that are requested by the BLIF or JSON and maps them to cells. This is why FPGAs are expensive. You can make a C compiler for an AVR in like a weekend or a couple of weeks if you don't really care about optimization, and it'll work. C compilers are really not that complicated. Place and route is a really hard problem. One of the things that the place and route tool that I use will tell you afterwards is, okay, I have place and routed this thing in such a way that you can run this main clock signal at no higher than 130 megahertz and it'll work. And you can tell it, I need to be able to run my clock signal at 35 megahertz, and it'll make sure that it places things such that the signal propagation times will be right. And that is typically a thing that computers don't have to worry about, but actual hardware does. Because place and route is a hard problem, it's frankly kind of amazing that there's an open source free tool that does it, much less two of them, one of which actually does it correctly, and it's not Arachne. I'll get to that. This tool is super complicated, and it is what Xilinx is charging a ton of money for. That having been said, don't use Arachne PNR. Ice Storm says that there are two PNR tools that it works with. One of them is called Arachne, one of them is called NextPNR. It doesn't tell you that you really want to use NextPNR. And I wasted most of Sunday trying to figure out that I really wanted to use NextPNR, because Arachne does not do tri-state pins. It just won't. Yosef supports tri-state pins. Yosef makes a glyph file that calls for tri-state buffers, it infers them correctly, they work fine. Arachne will not place and route them. And it will silently not place and route them. It caused you to waste an entire Sunday trying to figure out why. NextPNR places and routes them just fine and works great. So don't use Arachne, use NextPNR. Other than that, there's really not a lot of difference that I've noticed. These are both tools that take a thing that you're not writing directly and not putting another thing that you're not reading directly, so who cares? After that, there's a thing called Icepack. So the PNR file it's what NextPNR spits out is .asc. Wait, I don't know what that stands for. It's probably just ASCII. It's a list of where exactly on the die it wants to put all the elements that it's calling for. Icepack turns that into a binary bit stream. This is what actually goes on the ROM. So after you run Icepack, you're left with something .bin. You then need to get that onto your Fpga somehow. There are a few different ways to do that depending on the Fpga. This thing's actually got a whole separate data sheet, which is conveniently separate from the actual data sheet for the chips, so you don't think it exists for like 2 whole weeks. That will tell you exactly what it's expecting interface-wise from what's giving it the bit stream, which isn't a whole lot. It turns out that what it expects is an SPI chip that it can send a command of 9B to, and then keep on sending zeros and getting back bytes until it reaches 32K. These flash chips are commodity items. I think this one costs 17 cents. It's not a big deal. You'll need something to write to a flash chip. There's a tool called Icepack that will, on a lot of dev boards, Icepack will write over USB serial to a flash chip and flash it. My board that I built doesn't have USB serial or USB anything. So I also had to build this widget, which I'm calling the Streak, because it's a flasher. This thing will talk SPI. It's nothing but an AVR microcontroller. It'll just bit bang SPI to talk to this SPI flash and put that bitstream on the board. And then you've got a board that, when it's powered on, or when it's reset, your chip will send that command to the SPI flash, load the bit stream, configure all those little logic elements to be whatever you want your chip to be, and then from then on it is doing that thing. It is not running a program. Like it is exactly as though you had a big complicated IC that is exactly what you described in your Verilog, assuming your Verilog is correct. So why is that so great? Why don't we just use a really fast microcontroller? I mean, an STM32 is like, what, 70 megahertz or something? And they're like, what, $5? Speed is a big part of this. Even a fast micro is going to run things on the order of microseconds, right? And a cheap microcontroller is going to run things on the order of milliseconds. This Fpga, I can comfortably run things in a couple of nanoseconds. The other thing is parallelism. A microcontroller does one thing at a time. It is fundamentally a computer that is running one instruction at a time. And if something happens when you're running this instruction that you want to deal with, then you can fire up an interrupt, or you can just do a really tight loop and poll things. But fundamentally, the thing is running one thing at a time. Or it can be a propeller, it runs 8 things at a time, whatever, shut up. The Fpga isn't really running anything. It is actually that device. Everything that you synthesize from the board is active all the time. Those gates are all really there responding to signals. So a good thing that we can do with a Fpga that we can't do with a microcontroller. The most obvious thing, and the reason why I learned Fpgas to begin with, is to generate video. Connecting a homebrew computer to a TV is a pain, because video is an incredibly data-hungry and hard thing to do. You can talk to LCD screens or something like that serially, and it'll look all right. You know, that's how the Game Boy works or whatever. But if you want to do, if you want to build an NES, then you got to talk really fast with a lot of data, and you need special hardware for that. If you go back to what something like Commodore used, or everything but the ZX Spectrum used, you have special hardware for it. And the problem is, when I first started designing my own computer, I started looking at what I was going to do for video, and I found the perfect chip for it. It had a bunch of registers you could talk to, you could tie it to the bus, you could write values to these registers, and they controlled things like, what sprite number 3 looked like, what the background color of sprite 2 was, the position of these things, and so on. And so all you got to do is set these registers, and it just generates an NTSC signal that you plug into a TV, and it'll show these different colored things moving around the screen. It was great. It was called the Commodore VIC, or the Commodore VIC, video interface chip. Moss made it. It was the core of the Commodore 64. Moss went out of business in 1992. And no one's made a video interface chip, as far as I can tell, in 25 years. So if you can't make your own computer, make your own chip. VGA. VGA is now a generic video connector, basically, is what VGA means anymore, is this shape of plug. Video graphics adapter, it originally was an actual card, or an actual chipset. This thing here in the bottom right corner, that big chip, that was the VGA. In 1987, it was the video system for the IBM PS2. Is anyone here younger than VGA? Just out of curiosity? No, Aspen was, and I put that line in just right on it. Everything since then has cloned the VGA. It was a phenomenally successful standard. The product was really, really simple to implement. You can do it in a few lines of Verilog. And aside from just being easy to implement in hardware, it's also a really convenient standard to extend. There have been a gazillion different VGA modes. First was Super VGA, then XGA, WVGA, QVGA. I've got a phone book-sized manual at home, the programmer's guide to the EGA, VGA, and Super VGA chips. That is everything you ever didn't want to know about VGA, and it goes into excruciating detail and all this stuff. It's a really handy book, actually. But at core, VGA is incredibly simple. You got 5 signal lines. H-sync and V-sync are high when you are currently drawing visible crap on the screen. Kind of. So you get 640 columns, 480 rows. You're going to draw an entire row, then have an H-sync low period, then an entire other row, then an H-sync low period, and so on. You draw 480 rows, then you have a V-sync low period for a bunch more rows, and then you start over again. When you are currently drawing a row, you're going to have 3 red, green, and blue lines. You vary them between 0 and 0.7 volts, between all the way off and full-on bright. And by mixing those 3 colors however you want, you get whatever colors you want. It's an entirely analog signal. 640 by 480, all monitors were that shape back then.
I'm here to help. A little signing.
So 60 frames a second, 640 by 40, works out to exactly 25.175 megahertz, or roughly a little under 40 nanoseconds per pixel, which means that Arduino digital write ain't going to get it done. You need to go way faster than that. You need to be able to reliably produce data on those RGB lines every 40 nanoseconds. Trivial for an Fpga to do. This thing, the design that I've got on it now, will run up to 130 megahertz, which is way faster than I want it to, but... So, to write the code for this thing is a little different style. For a computer, what you do is, a for loop, or 2 nested for loops. You're going to iterate over each row. For each row, you're going to iterate over each pixel. For each pixel, you output a value. If you had a really fast, could run something so that it's outputting things at 40 nanoseconds per pixel machine that you were going to bit bang FPGA, that's how you would do it. For an FPGA, the coding style is a little bit different, and it's been actually fairly hard to adjust to. You don't have a loop, because everything you write is running all together at the same time. Instead, you've got a clock signal. So one of the things on this board that I've made is this little probably can't see it, the little silver widget here. This is a little thing that costs about 75 cents that if you hook it up correctly will output a square wave with a frequency of 25.175 megahertz. And so this is tied to one of the input pins of the FPGA. There are 4 special pins on this FPGA that are called clock pins. The only thing special about them is that the FPGA datasheet guarantees that a change on a clock pin will get propagated to every other cell on the chip within some ridiculous number of picoseconds or whatever. So you got a clock. And you can put a thing in saying, put a thing in your Verilog saying, whenever this clock has a rising edge, then do something to these flip-flops. So increment a counter. If the counter is a certain value, set things appropriately. So I'm going to walk through sort of how a VGA sync module works on this FPGA, and then I'm going to go to past the slide deck, sort of what I've done in the past 2 weeks past that point. So Verilog is made up of modules. A module is kind of like a chip. So what you're going to do is define what the quote-unquote pins, although they're really called signals in here, what these signals of this chip are. You can have input and output signals. You can even have in-out signals that are both, which is where you can get into tri-state buffers, which I'm not going to talk about. So I'm going to make a module called Vga Sync. This module's job is to generate the H-sync and V-sync signals, and to also generate a bunch of other signals that, when taken together and interpreted like a big binary number that's 10 bits long, will tell me what row and column the thing is currently drawing. Then I'll have another module that reads those active and active row and active call signals and draws some color pixel based on that. So my module takes in a clock, because it's got clock input and it's got these things outputs. It's got an active. Active is going to be a high value if we're currently in that part, in the top left part where we're actually drawing pixels. It's got an active row and an active column. Those are going to range between 640 and 0 and 639 and 0 and 479 for the screen. So the actual screen is 800 by 525 when you count the dead zones. And so what we're going to do is just have a total calls and total rows, and then have a big, essentially Boolean statement, just to, a bunch of comparisons to those constants to see if we're in the active area or not. So these things here, these assign lines, this is what's called a constant assignment. So this is the simplest way to tie things together in FPGA. What assign does is draws a wire between 2 different nodes of the circuit. And so whenever one of these things changes, the other one is going to change automatically. It's not like it would be in C where you're, whatever this variable is right now, copy its value to this variable. No, you're connecting these things together electrically. When this thing changes, this does instantly as well, or as close to instantly as the FPGA can make it. So this would generate the H-sync and V-sync and active signals. So we need another part of the code to read those signals. So this is what's called an always block. This is how you do clock logic. So always at pos edge clock, what that means is whenever the clock signal goes from low to high, then you're going to run whatever's in this block here. And whatever's in this block is going to use that kind of equally arrow symbol there to assign a value to a thing that's in a register, which is like a flip-flop. It's going to decide what this flip-flop value will be for this tick of the clock. And then next tick of the clock, we're going to assign something else to it, and so on. And so if call equals total calls minus 1, then we're going to, if row is total rows minus 1, so if both those things are true, then we've reached the end of the frame, we set things goes to 0. Otherwise, we increment row and then set column to 0. So we've reached the end of a row, we're going back to the left side of the next row. Otherwise, if we're not at the end of a row, then we're somewhere in the middle of a row, so we're just going to increment column and be done with it. Sorry, it's been a few days since I've actually gone over these slides, so I'm going to kind of read this code again as I'm going through it. So this is doing essentially the same thing, but for just the visible area, because it's easier for a programmer in whatever is going to consume this module to understand just the pixels in the visible area. So here's a way that you might use this module. So I want to be clear that a module is not like a function would be in a piece of software. When you call a function, that function call only exists for while it's currently running. When you instantiate a module in Verilog, that module now exists on the chip and is there for the entire program. It's just a chip that you have put in your design. So we're going to instantiate one of these things, which I didn't show that code here. We're going to instantiate one of these things, and then tie other stuff to the active row and active call signals and the active signal. So this is going to draw something kind of like a Texas flag. So if you look at it, if active, then we're going to do some stuff. Else, then red, green, and blue are all going to go to 0. Well, one of the things the VGA requires is that when you're not drawing, then R, G, and B all have 0 volts. It's a calibration thing so you can figure out what the voltage range is. But if you are active, then if the column's less than 200, then you make it all blue. Otherwise, you make it either all white or all red. And so you end up with a blue column on the left side of the screen, and then a white bar and a red bar. And I was not going to draw a star in Verilog. So one of the things you can do from here, most obvious one is memory, which I wrote this slide deck when I was still doing this on the dev board that I was using, like not this one, but the one, which, and I should mention also, if you want to start on FPGAs, there are a bunch of different boards that claim to be, great for people to learn FPGAs and all this stuff. Only one of them, as far as I can tell, is actually right about that. It's a thing called the Go board. They're $65 at a site called nandland.com. Nand like a NAND gate. Nandland.com. The great thing about it uses this exact chip. It's got a VGA connector on it. The great thing about it is that he has extremely in-depth tutorials that take you through such things as, here is how you install the Lattice tools, and here is the exact, make your window look like this one, check all these options and so on to upload your bitstream to the board. Because that stuff is not at all easy to figure out in the software. And he also teaches you Verilog step by step, and it's really quite a good board. It's the exact same chip as this, and actually it's a lot of it is the exact same circuit as this, because he also makes the schematics available. So one thing his board does not have is any external memory. So his chip only has the block RAM that is available on the chip, which is 8,192 bytes. You can divide that up however you want. It's it's just a bunch of flip-flops. There it is. But if you want to store more video than that, then you're going to need to have more memory. So I made my own board, which is this one. This has a 1 megabit chip on there that I can store plenty of video on. And so I will now go into a little bit kind of beyond this slide deck, because this is stuff I've done since then. Let me, is that at all legible? Okay, hope so. So what I've been doing, the eventual goal here is for this thing to be a video input device for a video output device for a computer. So let me actually put up the schematic. So the thing that I did here is I made the same circuit, minus all the stuff that's not video, and then I added in this 1 megabit RAM chip. The idea here is that I'm going to be able to store pixels on the RAM chip and splat out to the screen. There's also enough pins here for a nice little tie it to a Z80 or a 6502 bus, 8-bit interface thing. You can talk to it like one of those LCD screens. It's got a data instruction. 1 megabit is an interesting number. It is not quite I guess I should start with, like I said, I'm not really planning this part of the presentation at all. This is just what I've been thinking about the past couple of days. The ideal world for me would be I can asynchronously write commands to this thing to set a target pointer in that chip, and then write a byte and increment that pointer. I can also set a data register somewhere in there, a status register somewhere in there to set what mode I'm displaying, anywhere between 320 by 240 at 8-bit colors to 640 by 480 at 8-bit colors, to have multiple buffers and show change which one I'm showing at any given time, or have different text modes or whatever, and change fonts and things. I want to go nuts with it. Most of that's not really possible. And a lot of it is that 1 megabit is just not a whole lot of video RAM. 1 megabit at 8 bits per pixel is plenty for 320 by 240. That requires 76,800 bytes, which is fewer bytes than I have, but it's more than half the bytes that I have, which means that I can't do any kind of double buffering or anything where I'm writing to one buffer and then displaying another one. If I want to drop the color depth and do 4-bit colors, then I can trivially do that. I also can't do 640 by 480 at 8-bit color. That's too much. I can't do 640 by 480 at 4-bit color, but I can at 2-bit color. That'll work fine. Text mode I can do too. Text mode is 80 by 25 by 1 byte per character is not a whole lot, and so that's there's plenty of room for text in there. I will eventually make some kind of text thing. What's concerning me right now is, so right now with this thing, I can read from this RAM and display stuff at 320 by 240 by 8-bit pixels. What I can't do is write to the RAM. Actually, before I talk about that, I want to talk one more thing about this board. So Fpgas are essentially digital devices. I can have an output pin set to either high or low, ground or whatever the voltage supply for that pin is, which they're all 3.3 on this board. So I need to turn a bunch of digital I/O pins into an analog voltage. The thing that does that is called, quite appropriately, a DAC, a digital to analog converter. You can buy DACs that will take in 6 input pins and output an analog voltage that are discrete devices that do that. You can do what I did here, which is build your own with a bunch of resistors.
Can you do ADC?
I could put an ADC on this board. The Fpga itself doesn't have an ADC. The Fpga has a bunch of digital I/O pins. So this DAC, what this is for red, green, and blue, I've got a 2K resistor, a 1K resistor, and a 549 ohm resistor. And so depending on which of those pins I light up, it's going to combine to somewhere in 8 discrete voltage levels for that color. So that gives me a total of 9 bits per pixel. I cannot display, a very subtle shade of peach or something. I just can't make that voltage. If I had more bits per pixel, I could, but that would be more resistors, and then it'd also be more precision value resistors. The more bits you want to add to a DAC like this, the more you care about the value of the resistors. This one is kind of, a garbage DAC. This will work fine for the kind of machine I'm trying to build because I don't really care that much about graphics. The VGA connector, the original IBM VGA, had an 18-bit DAC, which is really nice. You got 6 bits each for red, green, or blue. But forget that for a minute. I've got 9 bits per pixel. I want to be able to store a pixel in 8 bits. Someone's got to give. It turns out that the human eye sucks at seeing blue. And so we are less sensitive to seeing things that are blue than we are to seeing things that are red than we are to seeing things that are green. We really like seeing green to a little bit less of a degree red things. Blue things, if all you can see is blue, it's going to look kind of mushy and blurry to you. JPEG, the JPEG format uses this to great effect. The JPEG format will do 1/4 of the resolution at blue that it does at red and green. And you can't tell. So I'm going to do a little bit like that. I'm going to tie the low 2 blue pins together so that I will have, only 4 values of blue, but I'll have 8 values of red and green. So now I've got 8 bits per pixel. And you can't really tell. For 4 bits per pixel, then what I'm going to do is, there are a few different ways of doing it. You can do paletted, which is you've got a full set of 9-bit, this value of 16, or this value in 4 bits corresponds to this 9-bit actual color, and then offer instructions to change the palette. You can also do what a lot of systems in the 80s and 90s did, which is RGBI. You have 1 bit each for red, green, blue, and then 1 bit for intensity, which either makes all of them brighter or all of them dimmer. It actually doesn't look half bad. The weird thing is that, especially with pixel art being so trendy right now in video games, none of these really look that bad. They don't look like total garbage. You can make a decent looking style for your graphics with almost any totally garbage way of doing graphics. Anyway, that's kind of a sidetrack thing about the whole graphics quality thing. The modes that I would like to target, I'd like to have 320 by 240 because it is, I can't do higher than 640 by 480 because of the clock and because of the VGA signal. If you double the pixels on that, you get 320 by 240, which has a couple of benefits. It fits nicely in the space of RAM. It looks pretty good to me, at least, because it's the kind of graphics that were in games when I was a kid. And VGA 320 by 200 was all the rage. That's what all DOS games look like. I would like to be able to do 128 by 128 by 16 colors with a set palette, because that's what a fake machine called the Pico 8 uses. I can't duplicate the Pico 8's palette exactly, because again, really garbage jack. But I can make a screen like that, and I think that a bunch of cool games have been made with that. I think that's a nice little format. Plus, that has the benefit of it just barely fits on the FPGA itself. You don't need anything but the block RAM to do it. Text mode would be great also, since I hope to sell these things at one point, and being able to type out "Hello World" on one with not a whole lot of effort is a really handy feature. And a super high res, 640 by 480 by 4 color mode would be awesome. The current thing that I'm struggling with is every cycle I need to spit out a pixel. But that leaves really not a lot of time left over for writing pixels to RAM. Because every cycle I've got to read the RAM. My clock is my pixel clock. I can't run things any faster than pixel clock, which I could, with a little bit of hassle. I could make what's called a phase locked loop, set the clock up to something higher, and then have 2 clock cycles per pixel, which would be awesome. And I might actually give up and do that, but I don't think I have to, because if you're doubling every pixel, then all of the odd numbered columns are the same value as the even numbered column that came before them, which means you only need to actually read the RAM half the time, even in the active part of the screen. Of course, in the inactive part of the screen, you can do whatever you want. So during the horizontal and vertical refresh periods, you have full access to the RAM because you're just setting zeros for the pixels no matter what, which is exactly the original, Darko knows about this, the original ZX81 did not have special hardware for video. It didn't have special hardware for anything. It did video in software, and did everything else during the horizontal and vertical refresh periods. This thing could have an extra pin here that would go high or something when you're able to write to it during a refresh period, and you can do the stuff that way. The problem is that even at that same clock speed, that means you still can't... that means that it would take... Because the refresh period is less total time than the active period in a frame, that means that it takes more than one frame to draw one frame. So no matter what you're doing, you're going to get crappy looking torn frames, which is already going to be a problem essentially because we have no double buffering, but why make it worse? But by writing in the back half of every pixel, then you're fine. Interestingly, this does not break down at 640 by 480. Because although you are still having to provide one pixel every clock, And so you know, the odd columns aren't necessarily the same as the even columns. Because it's 2-bit color, you still only have to read every 4 pixels, because you're reading a byte at a time. And so you actually get twice as much time to write in high res. Interesting thing. The real problem here, and what I didn't get to last night, I really wanted to have a demo where I could show this thing displaying an image. And what I didn't get to last night was displaying an image because of that writing thing. The writing clock is not necessarily the same as the video clock, because this is going to be used by a computer on a separate asynchronous clock. This is a peripheral device. If they were tied together, then it would be pretty easy to do. Because they're not, I need to make it where you can theoretically write a value to a buffer somewhere in block RAM, and then during the next time that it's possible to write something, write the next thing out of block RAM, and so on. That I have not actually gotten around to doing yet, because I've only had this board actually working for the past couple of days. I ordered the wrong clock component originally, the wrong oscillators, and so it was a few days where I realized that. I thought that I actually done the board wrong, and actually I got the part wrong. But yeah, it's only been like 2 or 3 days I've actually gotten to mess with this thing. But that's where I am right now. That's where I'm gonna go with it once I get a couple days free to finish it. I've been talking for a really long time, so ask me questions.
How do you express power of FPGA chip? Like microcontrollers say so many megahertz, so much flash memory and things like that.
Typically, what you get. Typically, there are there are 2 main metrics that they talk about, which is number of logic elements and number of I/O pins. Most of the time, you get most of the time these things go together. You get more I/O pins, or you get more logic elements. Because more I/O pins means a bigger chip, means more room for more logic elements. To a lesser degree, like they'll usually say, you know, this chip's got 1,024 logic elements. You'll need to look more closely to see how many of those are LUTs and how many are, you know, hunks of block RAM and how many are flip-flops. But usually LUTs, which stands for lookup tables, or just a number of logic elements. I want to say this one has got 1,024 LUTs plus some number of things. The other thing is phase-locked loops. This one has 1 phase-locked loop. Your more fancy ones have several phase-locked loops. A phase-locked loop is a way of stepping a clock either up or down, typically up. So if I wanted to turn my 25 megahertz clock into a 50 megahertz clock, then I could do that on this chip. If I want to turn it into a 12 megahertz clock, I could do that too. That's a lot easier. You just feed it to a counter and then use one of them.
What's the threshold of coming into this area of programming FPGA? You know, for microcontroller, for Arduino, you buy Arduino, you learn that sketch a little bit, and that you're there. So
I cannot say enough nice things about NANDland. Let me bring this guy's site real quick. Like this guy has, you know, really by far the best product as far as like beginner FPGA things. I wish I brought the board. I almost brought it. I thought I wouldn't be
you brought it once, I remember.
So what it is, it's the same chip that I use. He's got 2 7-segment displays, 4 buttons, USB for power and programming, and you can talk serial over it. This PMOD thing over here that looks like it's got 12 GPIO pins is actually only like 4 GPIO pins. It's kind of weak in the GPIO department. But other than that, I mean, if you just want to learn Verilog, this thing is great. It is the closest thing that I've found to the Arduino for FPGAs. I would say that is probably like the threshold, you know, simplest way of getting into it. There are some other ones. There's one called Tiny FPGA that I was into for a while, but I kind of got disillusioned with. They kept saying they're going to have, you know, fancy open source tools for programming it that never seemed to materialize. As far as putting them on a board, like putting a microcontroller on a PCB design is super easy. Putting an FPGA is a little bit harder. This thing needs 2 separate power supplies, a big ass diode for some reason. It doesn't need a clock source, but if you want to do anything clock, you need a clock source. And then you got the whole circuit with the flash ROM too. So it's a little more complicated than that, but not too much more complicated. The really nice thing about putting FPGA on a board is that you don't care which pins go to what. This is cool. So if you look at, check out the routing of the pins from the FPGA to RAM. Because I can assign whatever pin to whatever I want. So I just assign it so they made that nice pattern.
To make the etching really easy.
Made the routing take 5 minutes.
Is there a reason? Is it just that you're not moving fast enough that you need equal trace length?
Well, I'll say this, it works. This is like I said in the beginning, I'm not an electrical engineer. I majored in computer science. I don't really know what the hell I'm doing. I imagine at some point that will come and bite me, and I was halfway afraid that 25 megahertz was going to be that point. But it works. So,
What's the RAM normally has like a nanosecond rating?
you know what? I know the answer to that. I looked it up. Let me go to Master real quick and find out.
Oh, well.
That is a good, relevant question. That's why I'm going to look it up. That is not a stupid question at all. Because for video, you need to care about this. For processing, you generally don't. Because like, if you look at, your average M cycle for a Z80, you got like 100 or something nanoseconds. You got plenty of time. For this, you got 40 for the whole shebang. This RAM,
40. Well, I haven't found any RAM chips to get that fast yet.
this one does.
They're usually specialized just for video.
Yeah.
1 megabit.
It's why you have GDDR spec RAM on graphics cards rather than DDR.
This is 1 megabit, 10 nanosecond, 128K by 8, fast async SRAM. And I can speak for the fact that it is async, because I was doing that last night.
What's that mean by async?
Async means that it doesn't have a clock pin. So let me show you the Verilog. You're actually full of good questions tonight. So if you look at my Verilog down here, come, gaze upon my awesome Verilog. VRAM address, oh no, I changed it. Never mind. So right here, what I'm doing is giving VRAM address bus for this clock. I'm going to give it this new value of the column shifted over by 1 plus the row shifted over by 1 times 320, right? So I'm just going to count left to right, top to bottom pixels, starting at 0. And I'm using this little sort of arrow equals thing that's going to do it's going to load a register. Now, I don't have to make this a register. I could do that same assign thing that I showed you before. I could do a continuous assignment on this. And then as VGA call and row changed, VRAM address bus would just magically change along with it. And because this is async RAM, that would work. As long as that read pin is low, however the address pins change, the output pins will change accordingly. You don't need to, the data pins on output are not latched or anything with a clock.
I've never seen a clock pin on a RAM. Like the one in here, it has a chip select and an output enable.
You've only seen async RAM.
Oh wow, okay.
They do make synchronous RAM. They also make, and that's actually something that I wanted to mention, that they also make dual port RAM. Dual port RAM is exactly what it sounds like. You have 2 sets of address pins, 2 sets of data pins, and 1 block of RAM. And so you can have the video hardware reading from one end and the I/O hardware writing to the other end, which is exactly what you want for video RAM, right? Because you got one set of things that needs to monopolize those pins and do only reads super damn fast. And you got one thing that wants to do reads and writes at a relatively sedate pace. So, block RAM on the FPGA is dual port, by the way. That's actually how I was doing that when I was just using block RAM. But this RAM is async, and so you don't actually, like, you can just keep, like, I'm actually assigning the enable to be high and the read and write to be always read. And then however I change that address bus, the data pins magically change. I don't need to mess with any clock pins with the RAM at all. There isn't one.
What is the effective refresh rate of the signal you're outputting? 60 hertz?
I'm outputting 5 signals. So
Sorry, I gotta go. I'll try to catch you fast.
So let me go back a little bit. Did I close that already? I did. I closed it already. So let me go back a little bit to my my slides again.
Sorry, I gotta head out too.
It was good seeing you guys. Man.
Yeah, thank you for the presentation. I'm glad I finally got to see it.
Yeah, no problem. Okay, so what you get is 640 by 480 frame at 1 frame every 60 hertz. Or 1 frame at 60 hertz. That is standard VGA. Now, because it's 640 by 480, and because of the dead periods also, the refresh times, it works. The pixel clock works out to be 25.175 megahertz.
So,
and would you believe it? EPO does not sell crystals that frequency because they're bastards.
I'm shocked. Shocked.
They sell NTSC ones. They don't sell VGA ones.
So because most displays that understand VGA also understand things like, 1080p24. Have you thought about running, like, say, 24 or 25 frame a second instead of 60 to relieve yourself of the color depth and memory issues?
It ends up being easier to speed up the clock in the FPGA, actually. If I really need to, I can always use that PLL, turn this 25 clock into a 50 clock, and then have two clocks per thing. And then I'm totally fine. But 24 FPS is really kind of slow and crappy. I'd rather have, and the other thing is I would also like to have, like, in my adventures trying to get the stupid Amiga to work, most things don't actually like having non-standard signals. Like what I'm actually using for this, for a test bench, is a cable that is VGA on one end and HDMI on the other that I got at Amazon. It was like $10.
Okay.
What are typical uses of FPGA, other than what you're doing?
Practically everything these days, honestly. It's sort of, so there's kind of like 3 tiers. There's really more tiers than that, but there's like, if what you're doing is you're making a whole bunch of something and you care a whole lot about clock speed, you do an ASIC. You do a custom chip that does that thing. If what you're doing is you are doing a whole lot of something and you don't give a damn about clock speed, you do a microcontroller, because those things are dirt cheap and easy to use. If you're doing a few of something and you don't really care about clock speed, you do a Raspberry Pi or some kind of system-on-a-chip thing, right? If you're doing like a medium-sized run of something and you care a lot about clock speed, that's FPGA. You don't have enough money to spin your own ASIC, but you also need to process signals on a nanosecond scale.
Maybe need to be a little more customizable than an ASIC would be. Like you might not have it exactly finalized.
Yeah. Like fairly often, also you might start with an FPGA and then once your design is finalized on the FPGA board, then get some foundry to turn that into an ASIC maybe.
Yeah. One of the issues you run into with ASIC is now you're dealing also with your silicon yields. And so it's not, hey, I need 10,000 of these. Great, we're gonna have to make 40,000 to get the 10,000 that are in spec, because you're, generally when you're doing ASIC stuff, it's, super, super fast.
Yeah.
And there'll be, some small error in the lithography that means, yeah, that one's no good.
So what's annoying, and this is kind of like I kind of alluded to this earlier, but you kind of got to lean into this at a certain point, is FPGAs have largely killed the VLSI chip industry. Once upon a time, a place like Moss could sell, a chip that just did sound and did really good sound, or a chip that just did video and did really good video. Now nobody wants that anymore. You just want to buy an FPGA, because then you can do everything all at once. So there are still places that do, super basic 7400 series glue logic. There are places that do, whole CPUs, things you center a system around. There are not that many places anymore, it seems, that do VLSI chips. Your I/O controllers, your things like that. They just don't exist.
I think a lot of it depends on application. Because you still see a lot of that stuff with DSP.
That's true. Yeah.
Yeah, that's what I was asking about specifically for that. So I'm trying to do some DSP with Arduino. So there is ADC, 8-bit, that's okay for me, 10-bit, that's okay for me, but it only has so much flash RAM. So you cannot put so many effects in the flash RAM. You can put 1 or 2 or maybe 1, and then whenever you need new one, you reload, or you have multiple Arduino chips. So I was thinking, if I can make custom DSP in FPGA and control how much memory I can have. So
Yeah.
that's possible, right?
Yeah, sure.
But
Yeah,
you need
the only
to
thing
learn
like the only
very
thing-
well.
Verilog, yeah.
Big barrier.
That's the threshold. That's the big barrier.
Well, the only thing you're gonna, the only thing you're gonna have problems with is you're gonna need to have external ADCs. I have not seen an FPGA that has built-in ADCs or DACs.
External ADC is okay. Once I get the big
Yeah.
number, I pass it to FPGA. For me,
Yeah, and that's exactly what you're gonna do.
Yeah.
And that's fine.
Mm.
The other cool thing, this is something that I read about. So there's kind of it's called a three-chip design for a 6502 computer. Well, this would work with a Z80 or really anything, kind of small, that scale. You got 3 chips. You got a processor, you got the RAM, and you got an FPGA doing all the bus control, everything else, all the peripherals. And the FPGA sits between the CPU and the RAM. And so it does all the address decoding.